Welcome back to Research Unraveled, the podcast where we explore the cutting edge of artificial intelligence. I'm your host, Alex, and today we have the pleasure of welcoming Maya, a leading expert in AI and natural language processing. Maya, welcome to the show.
It's great to be here, Alex. Thanks for having me.
Today, we're diving into a fascinating research paper titled Large Language Diffusion Models. Now, that sounds pretty technical. Can you break it down for our listeners?
Absolutely. At its core, the paper challenges the long held belief that autoregressive models, or ARMs, are the only way to build powerful large language models, or LLMs. Think of models like GPT-3, GPT-4, or LLMA. They all use this autoregressive approach.
Okay, so ARMs are the standard. What exactly is an autoregressive model?
Imagine you're writing a sentence. An autoregressive model predicts the next word based on all the words that came before it, one word at a time. It's like completing a sentence sequentially. That's why it's often called the next token prediction paradigm.
Got it, so what's the alternative proposed in this paper?
In this paper, they introduce LLaDA, which stands for Large Language Diffusion with Masking. It's a diffusion model trained from scratch. Instead of predicting the next word, LLaDA works by masking words in a sentence and then learning to predict those masked words simultaneously.
Masking, like blacking out words and having the model fill them in.
Exactly. Think of it like a fill in the blanks exercise, but on a much larger scale. LLaDA uses a process where it gradually masks tokens in a sentence until it's completely masked. Then, it learns to reverse this process, predicting the masked tokens to reconstruct the original sentence. This is done iteratively, refining its predictions at each step.
So it's not predicting one word at a time, but rather looking at the whole context and filling in the gaps. That sounds different. What's the advantage of doing it this way?
Several advantages. First, it allows the model to consider bidirectional dependencies. Arms are inherently left to right, which can limit their understanding of context. LLaDA, because it can see the entire sentence, can better grasp the relationships between words, regardless of their position.
That makes sense. So how does LADA actually learn to predict these masked words?
It uses a transformer architecture, similar to what's used in many arms, but without the causal masking. This means it can see the entire input sequence. The model is trained to minimize a loss function that essentially measures how well it can predict the masked tokens. This loss function is derived from a likelihood bound, which ensures that the model is learning a good representation of the underlying language distribution.
Okay, so it's trained to be a really good fill-in-the-blanks expert. What were the results? Did it actually work?
That's the exciting part. They scaled LLaDA to an 8 billion parameter model and pre-trained it on a massive dataset of 2.3 trillion tokens. The results were surprisingly good. LLaDA demonstrated strong scalability, meaning it got better as they increased its size and the amount of data it was trained on. It performed comparably to our self-constructed ARM baselines trained on the same data.
Comparable to ARMS, that's impressive. What about specific tasks?
They tested LLaDA on a variety of benchmarks, including language understanding, math, code, and Chinese language tasks. Remarkably, LLaDA 8B was competitive with strong LLMs like LLaMA 38B in in-context learning. And after supervised fine-tuning, or SFT, it showed impressive instruction following abilities in case studies like multi-turn dialogue.
Multi-turn dialogue, so it can actually hold a conversation.
Yes, they found that LLaDA could effectively retain conversation history and generate contextually appropriate responses across multiple languages. This is a significant achievement, as it demonstrates that diffusion models can achieve conversational AI capabilities that were previously thought to be exclusive to ARMs.
Wow, so it's not just filling in blanks, it's actually understanding and responding. You mentioned instruction following. What does that mean in this context?
Instruction following refers to the model's ability to understand and execute specific instructions given in natural language. For example, we could ask LLaDA to write a poem about life choices, with each sentence starting with the letter C, and it would generate a poem that meets those criteria.
That's pretty sophisticated. You also mentioned something about the reversal curse. What's that?
The reversal curse is a phenomenon where arms struggle with tasks that require reasoning in reverse. For example, If you train an ARM on the sentence, A is the capital of B, it might have difficulty answering the question, what country has A as its capital? El Lada, because of its bidirectional nature, is less susceptible to this curse.
So it's better at understanding relationships in both directions. How did they test that?
They used a dataset of famous Chinese poem sentence pairs. They tasked the models with generating the subsequent line or the preceding line. LLaDA showed consistent performance across both tasks, while ARMs like GPT-4o struggled with the reversal task.
That's a really interesting result. It suggests that LLDA has a more balanced understanding of language. So what are the implications of this research? Are we going to see a shift away from ARMs?
It's too early to say for sure, but their findings open up new possibilities for exploring alternative probabilistic paradigms in natural language processing. Diffusion models offer a different set of trade-offs compared to ARMs. They might be better suited for certain tasks, such as those requiring bidirectional reasoning or handling longer contexts. I think we'll see more research in this area, exploring the strengths and weaknesses of both approaches.
What are some of the limitations of LLDA, and what are the next steps for this research?
One limitation is that they haven't yet scaled LLaDA to the same size as the largest arms. They also haven't fully explored techniques like reinforcement learning for aligning LLaDA with human preferences. Future research will focus on scaling LLaDA further, exploring different architectural optimizations, and investigating its ability to handle multimodal data, like images and audio.
It sounds like there's a lot of exciting work ahead. Maya, this has been incredibly insightful. Thank you for sharing your insights on this research with us.
My pleasure, Alex. Thanks for having me.
That was Maya shedding light on the potential of diffusion models in large language models. Join us on Research Unraveled as we continue to explore the ever-evolving world of AI.